Welcome to our presentation. We designed a deep convolutional network for the segmentation of biomedical images, which we called UNet. It learns to segment images in an end-to-end setting, which means a raw image in and a ready segmentation map out. The main challenges were that we had only around 30 annotated images per application, and we nearly always have touching objects of the same class that need to be separated by the segmentation algorithm. Here is the architecture of our UNet. Like all other convolutional networks, it consists of a large number of different operations illustrated by these small arrows. The input image is fed into the network here at the beginning. Then the data is propagated through the network along all possible paths, and at the end, the ready segmentation map comes out. Each blue box corresponds to a multi-channel feature map. The XY size is denoted here, and the number of feature channels is denoted here. Most of the operations are convolutions followed by a nonlinear activation function. In detail, it looks like this. It is a standard 3x3 convolution followed by a nonlinear activation function. An important design choice is that we only use the valid part of the convolution, which means that for a 3x3 convolution a 1-pixel border is lost. This allows later to process large images in individual tiles. The next operation in the UNet is a max pooling operation. It reduces the XY size of the feature map, so I have illustrated it as a downward arrow. The max pooling operation acts on each channel separately. It just propagates the maximum activation from each 2x2 window to the next feature map. After each max pooling operation, we increase the number of feature channels by a factor of 2. All in all, the sequence of convolutions and max pooling operations results in a spatial contraction where we gradually increase the what and at the same time decrease the where. A standard classification network ends here and maps all features to a single output vector. The UNet has an additional expansion path to create a high-resolution segmentation map. This expansion path consists of a sequence of up-convolutions and concatenation with the corresponding high-resolution features from the contracting path. This up-convolution uses a learned kernel to map each feature vector to the 2x2 pixel output window, again followed by a nonlinear activation function. That's it. The output segmentation map has 2 channels, one for the foreground and one for the background class. Due to the unpadded convolutions, this map is smaller than the input image. The segmentation of the yellow area uses the input data of the blue area. With an overlap tile strategy, we can segment arbitrarily large images. At the border, we extrapolate the data by mirroring. The main challenge in biomedical image segmentation is the low number of training data. To teach the network the desired robustness properties, we apply random elastic deformations. The resulting deformed image looks perfectly like an original image. If I remove the green grid lines here, the deformed cells cannot be distinguished anymore from real cells. The second challenge are touching objects of the same class that have to be correctly separated. Here we insert background pixels between all touching objects and assign an individual loss weight to every pixel. This allows a strong penalization if the network accidentally closes these gaps. We trained the UNet for the segmentation of neuronal structures in electron microscopy. The challenges in this dataset are structures with very low contrast, fuzzy membranes, and other cell compartments. We achieved a new best score in terms of the warping error, which was much better than from a sliding window convolutional neural network. Furthermore, our network is very fast. The training time was only 10 hours and the application is about 1 second per image. We also participated at the ESB Cell Tracking Challenge 2015. One of the datasets contains cells in phase contrast microscopy. They show strong shape variations, weak outer borders and strong irrelevant inner borders, and the cytoplasm has the same structure like the background. The output of the UNet is shown in cyan here and the ground truth in yellow. We won on this dataset with an intersection of a union of 92%, while the second best method only reached 83%. Another dataset was even more challenging. It contains touching and overlapping cells, partially invisible borders, and the cells leave the focal plane. Here we won with an even larger margin. More details and the implementation are available on our homepage. Thank you for your attention.